Hello, everyone, and welcome to another exciting version of Chip Talks. Today, we're going to talk about mitochondrial health. I've done some past Chip Talks on mitochondria, and I've called them the philosopher's stone. I really believe that they are. I believe that as we understand the mitochondria and kind of what they need and what they want and how they function, that'll be one of the real secrets to health and real secrets to helping us understand our function. If you have healthy mitochondria, it's really hard for you to have an unhealthy cell. If you have healthy cells, it's really hard for you to have an unhealthy organ. If you have healthy organs, it's really hard for you to be unhealthy. So that's why it's so important to talk about this stuff, is because we kind of got to start from the ground up. When we look at human function, we look at how you work, we have to start with these most basic, most, let's say, critical systems, and then rebuild human function from there. So the endocannabinoid system is a giant part of that exercise because it is such a basic part of how we work and how we function. Cells, obviously, are such a basic part of how we work and how we function. So we have to understand what a cell needs. And people ask me all the time, Chip, why are you so confident in what to eat and kind of eating behaviors and things like that? And I just understand, I've studied what a cell wants and needs, and that's really what it's all about. So you can put all kinds of food in your mouth, but ultimately you're really just defining that and distilling that down into what a cell needs. Okay, so let's jump into mitochondria. And again, I've called these guys the philosopher's stone because I think that they really are. I think that if you understand mitochondria, you understand life. And what happened a long time ago is a cell, like a eukaryotic cell, and we're mostly eukaryotic cells. So there's really three types of life on the planet. Okay, so there's eukaryotic type cells, and that's what we are. And that's what most things that aren't, let's say, bacterium are. There's the whole class of bacteria, and then there's a class of things called archons, or which are really interesting and kind of in between, let's say, us and bacteria. But those are how cells are classified. Okay, so you can either have a bacterial cell, eukaryotic cell, or one of these archon type cells. Now, what looks like happened a long time ago, and this is really cool, is that at some point, eukaryotic cells can do something called autophagy. So if they're in an organism like you and they see something they don't like or something they want to get rid of, they'll just engulf it. They'll just Pac-Man it, right? So they're just literally like Miss Pac-Man used to do with all the dots. So they'll just gobble this stuff off. And then they have processes inside of themselves that help degrade whatever it is that they just gobbled up. Well, at some point in evolution, a eukaryotic cell gobbled up a little bacterium and decided to keep him, decided he was valuable, decided he was producing energy, and that might be super interesting. And in fact, life might have started at this point when you had a eukaryotic cell engulf a little bacterium to create a mitochondria. But mitochondria are the powerhouses of cells, and they're like their own unique little individual organism inside cells. So inside of, let's say, a heart cell, there might be thousands of mitochondria. Usually in science, just kind of the going number is 1,000. You just assume there's 1,000 mitochondria in a cell. Now, some cells don't have any mitochondria, like red blood cells. Why? Because they have to carry oxygen. And if they had mitochondria, the mitochondria would eat all that oxygen, because mitochondria use oxygen for fuel, oxygen and fat in us for fuel. All right, so let's break this down. Let's talk about mitochondria in detail. Let's talk about what they do, what they want, how they work, all that stuff, so that we can better understand them and also better understand, let's say, how they contribute to disease and how they contribute to the overall pathology of aging and things like that. So we have to understand these guys because they are literally what gives you and me life. Without mitochondria, we are plastic, we are cut wood, we are not living, we are not metabolizing, and you have to metabolize in order to be alive. So let's talk about the mitochondria. There's three different, and it's not like there's three different types of mitochondria, but let's say there's three different states that mitochondria want to run in. So the most basic state is something where they're producing energy from fermentation and glucose. This is a really fast exercise. So a mitochondria can do this really fast. Give me that glucose, bam, I produced energy. But it's not very efficient at all. So 1 unit of glucose kind of produces 2 units of energy. And that's not real efficient compared to some of the other forms of energy production. But that's a cell's default mode, if you will. It's the most basic way that a cell can metabolize. And it's something that a cell can do without, let's say, needing to have light in photosynthesis or needing to have fats and oxygen in fatty acid processing. And those are the other 2 ways that a mitochondria can produce energy. But in glucose mode, and I call it glucose mode or sugar mode, a cell is quick, but it's inefficient and it's not as powerful. It doesn't have the power to do multiple things. It just can kind of do one thing. So cancer cells actually operate in this mode. They kind of get stuck in between beta oxidation and glucose mode, but they operate in this mode. So they can rapidly reproduce. They can rapidly, expand, but they're not efficient at all in how they do it. So they're, eating, let's say, a bunch of amino acids and glucose from you when they're doing that. Some bacteria and things like that are also, if you hear, gram negative, anaerobic type bacteria. There's some bacteria that process oxygen and some that don't. And the ones that don't obviously have to run this mode. So mode 1 is glucose mode, super quick, but super inefficient. Mode 2 for a mitochondria is fat mode. And that's how we're really built to run. So we're built to run in fat mode, where our mitochondria are producing energy from dietary fats and from oxygen. And the way that they do this is they move electrons, okay? So we're gonna talk about this in a lot more detail here in a second, but they move electrons through 4 different processes. And when they do that, that creates potential and creates energy, okay? And we'll talk a lot more about that in a sec. The third way that mitochondria produce energy is through light and through photosynthesis. So we know this from plants, that plants produce energy from light. And in order to do this, you really have to have chloroplasts. So chloroplasts are what, let's say, are the variable energy things inside of a photosynthesizing cell. So they'll ramp up in energy release, ramp up in energy release, ramp up in energy release. And the mitochondria use this process to energize the entire plant. So that's the 3 modes. So glucose mode, fat mode, or light mode. In light mode, those mitochondria are a little different. They're a little bit more sophisticated, let's say, than our mitochondria. In light mode, you have to have some other guys in a cell with you. So you have to have a chloroplast for sure. In fat processing mode, again, you need some other guys in a cell with you in order to fat process. So you've got to have a perioxome and you've got to have an endoplasmic reticulum. Why? Because these guys help prepare fats for burning and help kind of get everything ready. And then they also bend and shape the fats as they're, let's say, processed. So endoplasmic reticulum folds fats, right? So that's what it does. Okay, so that's a little bit about the ways that mitochondria produce energy. Now, interestingly, we can control to a certain degree, let's say our global or macro mitochondrial energy states. And the way that we do that is by eating. So when we eat a meal, we go into glucose mode for about 5 hours. And why? It's because our cells are having to deal with the fat and they can't really be running on fat and dealing with the fat at the same time. Why do we need to deal with fat? Well, every time you eat a meal, fats are the most important thing to our body. Fats are king. Fats are king to a cell. Everything that you need to run you comes from dietary fats. So as far as a human goes, or mammals go, fats are king. And so those fats have to be processed in certain ways to be able to be put into, let's say, the mitochondria. And that can't happen when you're just have eaten. When you eat, again, there's an analysis that goes on between the fats that you just ate and what you have stored in your triglycerides. If what you have stored in your triglycerides is better than what you just ate, then there's not much action. If what you just ate is better than what you have stored in triglycerides, then you're going to be doing a lot of swapping out of your fat tissues in and out of your liver to reconfigure those triglycerides. And again, this happens every single time you eat more than 50 calories. So it's a lot of work. And when that work is being done, you want fast mitochondria, not efficient mitochondria. And so the mitochondria will run on glucose. 5 hours after we eat, our mitochondria will flip, and they will, and this is macro. Again, if you're running a marathon and just eating, yeah, the mitochondria in your legs and things are beta oxidizing, but this is just kind of at the macro level. So when we eat, though, we go into glucose mode, and 5 hours after we eat, because that's how long it takes to process everything, we'll flip back into fat processing mode. In fat processing mode, we're roughly 20 to 50 times stronger, more energetic, more, let's say, horsepower than we have in glucose mode. So glucose mode is fast, but it's not very powerful. Fat mode is slower, but way, way, way more powerful. So you could think of, in glucose mode, we're powering one house, and in fat mode, we're powering 25 houses. So does that matter to your immune system? Does that matter to your ability to defend yourself, to heal yourself, to think, to act, to work out, to do whatever? Absolutely, yes. And so we really want to be running, we want our mitochondria to be running in fat processing mode. So eating is consequential. And this is why we talk so much about intermittent fasting and so much about the consequences of eating. And it's consequential to your immune system. So if you're sick, again, you want your mitochondria running in fat mode. You want all of those 25 to 50 houses powered on so that you can heal yourself and fight off whatever's infecting you. If you have cancer, if you have things like that, again, we have no way to fight cancer when our cells are running in glucose mode. When our mitochondria are running in glucose mode, no way to fight cancer. None. Zero. Zip. Nada. 5 hours after you eat, when you flip into fat mode, you have two ways to fight cancer. You've got a process called autophagy, and you've got a protein called P53. So if you have cancer, this is super important. And again, you know, eating is consequential. You want to minimize the amount of time that you eat. You want to get your nutrients. Everybody needs to get their nutrients, but we want to minimize the time that we stay in that fed state. So the last way, the third way a mitochondria can work is in light mode. You know, you do some of this. We do. There's a whole realm of science called biophotons that's really interesting. So our mitochondria will, under certain circumstances, deal with and emit some light. Now, what can go wrong with mitochondria? Well, a lot of things. So when your body is under stress, let's say, what happens in the mitochondria, and when you're running on fat, it's complicated what has to happen. So there are 4 different enzyme complexes. This is called the electron transport chain, if anybody wants to look it up. And there are 4 enzyme complexes that basically we move electrons through these 4 complexes, and we're also moving protons. And when that, basically you're separating positive and negative charges, and you're putting membranes in between them. And when you do that, you create potential. So you can think of a battery like a 9-volt battery. So that's like a membrane with it's like a dam, let's say. Let's like a dam that is damming up all of this water. And the deeper and higher the water, the more voltage that you have, at least in a battery. And the same thing happens inside of mitochondria. So what you're doing is you're building a dam, and then you're beginning to, let's say, put water behind that dam to build potential, and then you release that dam, and that's what creates energy. So that's what happens through 4 different reactions in the mitochondria when we're in fat processing mode. Now, here's something that's super important. Well, a couple of things. So if you don't have those cofactors, like CoQ10 is a super important cofactor in how this works, it doesn't work. And what happens is electrons will leak. They'll leak out of the mitochondria, and this creates oxidative stress. The last thing you want is a little free electron, running around in your body, because guess what? He's going to react with something, and that might be a good thing or that might be a bad thing. But that's what reactive oxidative stress is. So ROS, and there's also a nitrogen side of this, RNS. But that's what happens when, let's say, there's a lot of inflammation. And when there's a lot of inflammation, there's intermediaries that have to basically grab these electrons and move them along, and they're called iron sulfur clusters. And these guys can get wrecked during inflammation. And if they get wrecked, then you can't move electrons, and you can't move electrons through these 4 different complexes. So these 4 different complexes, and let's say understanding what they are, understanding how they work, and making them the most efficient that we possibly can, literally is the secret to everything. It's the secret to no aging. It's the secret to very, very healthy life. It's the secret to, being the best you can be, hopefully looking like you're 40 until you're, 1,000 years old. Things like that. Again, those happen. Those secrets are found within mitochondria, and understanding what mitochondria need, want, and how they could go wrong. In neurodegenerative diseases, these are all diseases of the mitochondria. We might point to other things. We might point to other, let's say, insults. But what's really, really happening is the mitochondria are dysfunctional. In seizures, again, what is a seizure? It's a dysregulation of energy. Now, that can certainly be explained through nerve cells and how nerve cells are firing and their rest versus action potential. But at the core of all of that are mitochondria. Mitochondria power everything. They are the philosopher's stone. They're the secret to life. They're at the core of everything. Now, a real interesting thing that appears to be happening in our society, and this is just observation. So this is, you could, call this Chip's conspiracy theory if you want, but I could write you a peer-reviewed medical paper on this conspiracy theory. So I think it's pretty obvious and well established. And I think we're beginning to wake up to this. But for some reason, almost everything in our society wants to force us into this glucose processing mode. Okay. And what do I mean by that? And give me some examples of that, Chip. Tell me what you're talking about. Well, I'm talking about the USDA telling you that you need to eat breakfast, lunch, and dinner, and that, 6 small meals are better than, 1 big one, and things like that, because that's just wrong information. That's just information that is sending you down the wrong path, sending you down a path of inefficient function and the possibility of disease and all kinds of things. If we're in sugar mode all the time, how do we defend ourselves? How do we run our immune system? You have to run everything in you. You're a very complicated machine, plus run your immune system at 50 times less power or 25 times less power. It's just not going to work. Okay. So you're not going to be as robust as you could be if you're eating breakfast, lunch, and dinner. you're not going to be as strong. You're not going to be as able to defend yourself. So just that alone, is enough to change your life and change your health. Now let's look at some other things. So again, these guys need mitochondria need proper fats to run, and they need a proper kind of fat system. Those fats are associated with the endocannabinoid system. Now, the endocannabinoid system, if it's our master regulatory system, would have to have control over mitochondria because they control energy. So I'd have to have a way to turn you up and turn you down as to energy in the master regulatory system, if it really is the master regulatory system. And it turns out that there is such a way, and that actually works in practice. So every single, and this is fascinating, there is no system in your body where every cell will express a receptor for it, and not only every cell, but every organelle inside of every cell will express a receptor. And the only system in your body that does that is the endocannabinoid system. Why? Because it's the mammalian master regulatory system, and you have to have control literally down to every single cell, and not just every cell, every organelle. So mitochondria will all express a CB1 neuroreceptor on their outer membrane. Why? Well, it's a way to control calcium. And if you really look at how cells work, so there's a lot of, let's say, sophistication and nuance to a cell. But when you get just right down to the most basic way that a cell works, it's kind of positive and negative. So it's trying to do things with its cell wall. It's trying to change polarity inside so that there's more, difference between inside and outside, or it's trying to lessen that. So cells are always going through this process of having their walls more permeable or more locked up. And as they do that, again, they increase or decrease in potential and electric potential. And this is the way that cells work. This is the way that some cells move, but it's the way at their core that they work, is this electrical potential. Okay. And mitochondria are no different. Mitochondria are constantly messing with electrical potential. But this is all controlled through the CB1 neuroreceptor and through calcium. So calcium is positive, let's say, is a positive ion, so Ca plus, if you will. And what that means is that this is so confusing, and let's say electrical properties and stuff. You almost have to have your decoder ring to get it all straight. But calcium, since it's a plus, so it's a plus ion, what does that mean? Well, it means it's positively charged, and that means that it has, let's say, more protons than electrons, if you will. But the best way to think of it is that little plus sign is just a hole. It's an electron hole. So calcium is ready to accept electrons. Now, if you have a mitochondria that's going crazy and he's leaking electrons, that calcium will suck up those electrons. But that basically changes the polarity of the cell, and changes the polarity of the cell in relation to outside of itself, or the mitochondria in this case. But anyway, in order for the endocannabinoid system to have control over energy status, it would have to have control over every single mitochondria. And it does. Every single mitochondria will express a CB1 receptor on their outer membrane. So that's really, really cool stuff. And that further supports, let's say, the endocannabinoid system as our master regulatory system and our master control system, all the way down to mitochondria, which is cool, cool, cool. All right. What else do we want to talk about mitochondria? I guess a couple of things. Again, in sickness, like a way to make you sick is to mess with your mitochondria. Let's talk about autism real quick, because it's always good to have an example. So autism is a fascinating disease, but it's good to talk about and talk through with mitochondria. Autism is probably one of the most sophisticated diseases on the planet. Why? Because where's the insult? Is it due to infection? There are aspects definitely of autism that look like they're infection related. So you've got lots of inflammation, you got a whacked out immune system, you got a whacked out gut biome. Is it fat processing related? Yeah, it is, because delta 6 desaturase fits and starts. Autistic people don't build the immune system with the same robustness that we do, and this is why they need such a sophisticated gut biome. But this all of these things, and I could go down probably 30 different things here, but all of these things really lead back to mitochondrial dysfunction. And why would mitochondria be? It's really interesting. In autism, there's two major things that are common across all autistic people. And all autistic people have lower and you can't say this about, oh, they're infected. Oh, they have high white blood cell counts. Oh, it looks like Clostridium bacteria is doing it all. No, none of that is common. The thing that is common, though, is lower endocannabinoids. So all autistic people have lower circulating endocannabinoids. They also have a lower, let's say they have a higher rate of these iron sulfur clusters being destroyed. And again, this has to do with mitochondrial dysfunction. So the mitochondria in autism is always messed up, and that is the core and key thing. And it's now looking like it's a loop, that autism is kind of a loop between these, oxidative stress, which destroys iron sulfur clusters, which are necessary for mitochondrial function, and which are also necessary to build endocannabinoids. So it's a loop, but it's a bad loop, and it's a really consequential loop, let's say, but it is a mitochondrial loop. If you look at seizures and neuropathy, all of those things are dysfunctions in mitochondria. If you look at Alzheimer's, if you look at dementia, if you look at Parkinson's, those are dysfunctions in mitochondria. So it's really important that we get the mitochondrial story right. Now, one of the things that we're going to be doing, we've just come out with a new product in TrueMedics called Mito, and it's a tablet product. But I really want to come out with a powder product that is super powerful, and will feed the mitochondria properly. If you have healthy mitochondria, you're going to have healthy cells. If you have healthy cells, you're going to have healthy systems. If you have healthy systems and organs, you're going to be a healthy you. So it all kind of starts from the inside out. So watch for more information about mitochondria. Watch what we're doing at TrueMedics. Because we'll be coming out with more of these wonderful products. So right now, go find you some TrueMedics Mito. That's a very good product. Look at what's in it. Run that through whatever, situation you want to run it through to see if that will work for you. But I guarantee you it will work for you. And try that product. It will kick up the function of mitochondria. And this helps with everything. If I had cancer, I would want to be kicking up the function of my mitochondria. If I had any kind of neuro disease, I would be absolutely wanting to kick up the function of my mitochondria. If I had seizures, if I had neuropathy, if I had heart issues, the heart is run. What keeps your heart beating and beats at the rate that it does? Mitochondria. I mean, there's no more important place for mitochondria than in the heart. And the heart is probably the biggest user of mitochondria all the time. So super important to keep those guys healthy, because we want a long, healthy lifespan with a healthy heart. All right, we'll leave it there for today. We will see you guys back next week for another exciting version of Chip Talks podcast. Bye.